We have, first up, we have Cunningham, and he's pretty well known in this town because he goes to a lot of things and is interested in everything.
Mostly I go to the summer and winter social. That's where I can hit all the user groups all at the same time and they have booze.
Well, or you might also see him at like Bailey's Tap Room.
Bailey's is good. Dorkbot, I spend a lot of time at Dorkbot. And people know Dorkbot? Yeah, Dorkbot is worth checking out. But this is the place to be. So are you ready for me?
Yeah.
So, I brought this up just to make sure the computer worked. And I kept looking at that, and I said, nowhere on there did it mention assembly language. So this is kind of digging into my ancient past, trying to remember what it was like to program an assembly language. And I've done some assembly language more recently, and Daniel knows about it. And he said, why don't you talk about that stuff with the little tiny chips? And I said, well, I only do that really to remember what it was like in the old days when everything was in assembly language. And that was pretty cool. But what I really want to do is talk about taking those old programs that were worth it. And I'm not sure this one was worth it. I wrote it myself. But taking those old programs and remembering them in one way or another. And there is a strong preservation movement that hangs out with, not surprisingly, the Computer History Museum down in the Bay. And I was on their mailing list for a long time, and they're saying, well, first things first, let's just not lose them. And they call that preservation. And then they try to figure out all the ways you could lose old programs. And so you say, well, you just have to keep making duplication, many copies, duplication, get it on new media. And I thought, well, okay, so they can do that. I find that's boring. I got my punch cards on a 9-track tape and my 9-track tape onto a little Mac diskette and my Mac diskette onto Unix, and I haven't worried about it ever since. So that's
which one's going to last the longest?
Punch cards, probably the punch cards. There's another activity that kind of falls into this, and that's restoring, actually bringing them back to life, old programs, by simulating old computers. And if you got old Mac programs that you love or whatever, that's a worthwhile thing. But still, all you can do is experience being a user in the program. And because I'm a developer, I wanted to experience what it was like to write those old programs. So what I'm interested in is restoring the process of, I call it navigating. I mean, I can't even remember what text editor I used, but, just be able to move around in a big program and find parts of it and to see what's going on. And this is where I say, I don't actually care what registers are used, but I want to know how they were used, what was going on in those old programs. And in fact, I was interested in what goes on in new programs because I was there at the founding of the software patterns movement. And that was all based on object-oriented programming and stuff like that, all the latest and greatest. But at the time we're exploring all this, we're looking to say, well, what does it mean to be a pattern of software? And I kept thinking back to these old programs. They were old even then, and this was a long time ago, where there were a lot of patterns. And so I thought, well, gosh, let me see if I can restore one of those old programs and just annotate it with what patterns are present. So this first one is saving the bits. Second one is running the bits. And I call the third one knowing the bits, where you have some sort of insight into it. And I saw recently that NASA open sourced all the software from the Apollo era. He's smiling. Have you downloaded that stuff yet? Well, of course, this is the Apollo lunar module display keyboard, and I have a little bit of association with that because the guy, flying that thing down, and this thing's running out of gas, and it starts flashing up error messages, right? This is Apollo 11. He is a Purdue grad. Now he's at Purdue, and he came and spoke at Purdue, and he gave a nice talk about how cool it is to be an astronaut. And some guy from the computer science department says, well, what did you think when you're trying to land this thing on the moon the first time ever, and you start getting error messages out of your computer? And he said some nice things about the people who did the computers. Well, it turns out it's a great story because some guy back at NASA memorized all the error codes. And as soon as he said an error code, the guy says, go to land. And they just ignored the error codes and landed. Right? And that software is available for study now. And I think that would be restoration that's awesome because they're really brilliant people. One of the things that made that all work is the thing was getting interrupt overload and crashing. And someone in development said, you know, this is a really important program. Let's make sure if it reboots that it gets running again, the basic software in one cycle. So this thing would reboot in one cycle. They didn't pick this up at Microsoft, by the way. One cycle, this thing comes back up again. And so it was crashing, coming up, crashing, coming up, crashing, coming up. But it ran enough that it could land that thing on the moon. So a cool thing. So this is my restoration, and I thought, I'm going to take this old program, and it was a program that simulated a PDP-8. And so it's a program in assembly that was written so that I could run the PDP-8 assembler so I could write PDP-8 code without using a PDP-8. And it's a long way around. But it was also an experiment in all this, and this is 1998. The internet is still young, but not so young that we didn't have tables, and this was also my experiment in using tables to format a page. And so I'm really getting into this idea that there's a left margin that I can put information in. So I have plenty of left margin here. The other thing is, this is a PDP-8, and I wrote this code in 1975, which is really getting back there. And there were no personal computers, but I went to an engineering school and there were people who could pick up old broken ones and fix them. And that wasn't me. But the people who could fix them couldn't program them, and I could program them. So we would form some sort of alliance hanging out at the radio club, and that's a typical radio of the era and a typical terminal of the era. And that was enough to build a computerized radio, and that's what we were working on. The problem with this is, I don't know if you noticed, but there's no disk drive there. So this all ran off a paper tape, and you would run the paper tape into that reader on the left-hand side of the terminal and go ka-chunk, 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 reading about 10 characters a second. And the first thing you had to load is the assembler. And then you had to load your program, which you had typed on that terminal. And then you had to load your program again because it was a 2-pass assembler. So you had to run the tape through twice. And then if you wanted to save it, you had to punch a tape because there was a punch there too. Oh, that's reading it twice, and that's the punch. And this was really tedious. So I'd go over to my friend's house, and it was time to go home by the time we got the program assembled. So, but I worked for the university, and that was their computer, a big CDC, 6000 series supercomputer of the era. It took a whole floor of the basement. Actually, it took 2 floors of the basement, and it was a neat computer. It's one of the greatest computers. In fact, the people who ran digital equipment, when they got to reminiscing about computers, they said, "Oh yeah, that Seymour Cray and the CDC 6000 series. That was cool computers," and it was. But I could run that anytime, day or night, and I got on this other one evening a week. And so I'd feed my paper tape into there, and believe it or not, in spite of all those tape drives, it did have a paper tape reader punch. And they didn't actually like to admit it, because that paper tape went through so slowly that it used a substantial amount of computing resources just watching the tape move. It was also buggy, and I got the cool job of working on the bugs in the paper tape reader punch. But so there it is. I only had to read the programs in once. I saved them on there, and then I would punch out paper tape and take it over to my friend's house. This is what I was coding. This is assembly language. That's for the PDP-8. And I think all assembly language looks about the same. That's not the code that I want to show you tonight, this is the code that is the PDP-8 simulator, and that's CDC code, not PDP code. And I don't know if you can see it in the back. Doesn't it look about the same? So there's an operator and an operand, but the operators, there was a much richer set of operators. They had to include numbers in them because they had so many registers on the CDC machine. And the other nice thing about doing this is you really get close to the machine. You're pretty close to it just programming if your program runs. But when you simulate it, you have to like read every page of the manual to figure out what every bit does all the time. And so I got pretty familiar with this computer and the architecture. And this was unusual at the time because they had this thing that they were very proud of called the omnibus. And what that would do is you could plug any card anywhere because all the sockets were the same. And that was a new thought back then. And one of the sockets was just the card that hooked up the front panel, and that's all the lights and switches. So controlling the front panel was a big deal. And this is what it looked like inside. There's the omnibus. There's the front panel controller. And this is the other machine. This is a CDC machine. It had, instead of one register, it had 24 registers. And the cool thing is on the right there, it had all these different functional units. So it could be adding integers, multiplying floating point, do all at the same time. That's pretty common now, but it was Seymour Cray, really kind of figured that out. The other thing he did is for I/O, on the left-hand side there, it says peripheral processors. He had 10 peripheral processors in it. Each one was about as powerful as a PDP-8. And you would program those to move the tape drives or the paper tape punch or to light up the operator's console. So there's all those registers, there's those peripheral processor, and there's the operator's console, which was a kick-ass operator's console, not just one tube. I mean, everybody else had blinking lights, and this had a graphics tube and a good Space Lander game, by the way, and 2 of them. And boy, it was real prestige if you got to like type on that. And this is what it looked like inside. What a mess. But apparently, everything was so tightly timed that people would find Seymour Cray in there working on a machine with an oscilloscope checking the timing and wire cutters trimming it off inch at a time to get the timing to all balance out at the speed that it would work. So back to my simulator. This is my HTML document in the late 90s, and I apologize, but I'm just going to run through this document, and it's online, so you can read it. And I like to strip the browser off, so we'll just see the document. Slide down here. The first part says, first of all, I got to explain the instructions, and I have to explain what a simulator does. Well, a simulator fetches an instruction, increments the program counter, ready to fetch the next, and then jumps to dispatches to whatever the instruction is. So there's a register that holds the instruction called the instruction register. There's a register that holds the address of the next instruction, that's the program counter, and then everything else is just doing the program. But every machine has one of these. This is, I think it's technically called the von Neumann bottleneck or something. But it's, so if you're going to write a simulator, that's all you have to write. That and something for every other instruction. Because I had a lot of registers, I just said, well, I'm going to dedicate a register of the CDC machine for every register of importance, even ones you couldn't see on the PDP. And so the first thing you have to do is memorize this map of where everything is. And you don't get to use like names. You have to call it X3, X4, X5, and remember what those things are. So you always had that written down on a notebook. Then we get into the real code. Now this is where I'm starting to get inventive because I have HTML. And what I did is I took this little bit of bookkeeping off the top there and I just said parentheses bookkeeping. And if you want to see it, you click and it goes to another page and shows you what that bookkeeping is. Also, in the margin, this new technology, I could put stuff in the margin. I had a little flow chart that showed you what's going on because you could jump anywhere, but we were semi-structured back then, and we would always try to jump down unless it was a loop, and then we'd jump up. So the structure, the layouts of all the instructions were important. Here I click on fetch, and it explains that's a macro, and this is what the macro is, and a little note there about how it fetched 12-bit PDP words out of the 60-bit CDC words and kind of spread them across registers. Then if you click on, that next instruction is set ext4, and if you click on the S, it says, oh, these are all the set instructions. So I'm kind of explaining the instructions a little bit at a time, and I could click on more of those. Down at the bottom is the jump that's going to go and do something, and that's called the instruction dispatching jump table, and that's where that is. That's just explaining what the computer does. In fact, you don't even like to write that as comments because you just assume everybody knows the computer, because they did back then. But then there's the, well, what approach am I taking to this? And that's over here on the left. There's a little pattern, and that's the logo of the pattern repository, which was my website at the time. That's before I called it Wiki. And there's 4 different patterns on just this one page. And if you click on those, and the neat thing about a pattern is it says, here's a problem that every assembly language programmer is going to know. You're going to have that problem somewhere. And then it says, therefore, and here's a solution. So it's a problem and a solution, and it's a problem that I have on this page. That's the context. And then outside the color, I even explain a little more detail of how I used that pattern in this particular code. So I think this is the best comment there ever was, because it explains this, and it explains it in a way that's reusable to any assembly language programmer on this machine or otherwise. So another one there called progressive rotate. That's because I had a bunch of bits. I don't know if you remember that little instruction layout. There's bits that mean different things. And this is where in the details it says, you know, we're going to, the way you get us, well, the only thing you could test is whether a number was positive or negative, which meant you had to have the bit you cared about out in the leftmost bit, the sign bit of the word. And so you would rotate it around. Now, some machines only would rotate one at a time, and it's important that you do things in the right order or you waste a lot of cycles. This machine could rotate any amount, but just keeping track was hard. So I don't know, this is kind of tiny, but it says, whenever you do a rotate, you specify how much to rotate, and that's always written as where you want to be and where you are now in terms of rotating the word. I might have that backwards, but I even show it a little bit here. Here's a little thing. It says 60-bit word, bit 59 is a sign bit, 0 to 59. So it says I want bit 7 to be in the sign bit. So I say 59 minus 7, and that's the right amount to shift. And then the cool thing is then I need to check the next bit, and that's a test down here. And I say, okay, well, I was at 7, but I want to be at 8. So you do 7 minus 8, and then that does the right shift. And so there's this cascading through this code. Not in any way. Then I jump down here and check a few more bits and another bit. And that's this progressive rotation. And boy, if you were an assembly language programmer and you faced this bit decoding problem and you didn't know to just do this, you would do kind of crazy. Every if statement would be like 5 instructions, and it would just be silly. And if anybody looked at your code, they'd say, oh man, you don't know how to program, right? Because this was something you had to know. The jump table I already mentioned, but here's jump table described not as how the machine did it, but how you would think of it as part of a fetch and execute loop. This is all the instructions that did a PDP-8. Well, I say all of them, it's most of them. Well, it only had 8 instructions, and so I just put a little table here. I didn't even make you have to jump it up. These are the 8 instructions. 1, 2, 3, 4, 5, 6, 7. There's one more after that I missed. And naturally, a supercomputer can knock off a PDP-8 instruction in just a few steps. So this is the joy of assembly language programming, after you have everything laid out, that you just get to just do exactly what you want to do. Now, it got a little more complicated when we got into the complicated skip and if stuff, because again, we got all this bit stuff going on. And so here, I'm checking all the bits in order, but instead of doing jumps, I'm just skipping. I just jump, so it's called a skip chain. When I get over here, this is it's more decoding. This one, instead of skipping and around things that I want to do, this one is deciding whether you're going to do a jump. And so what I'm doing is I'm assembling a Boolean value. And this condition is not met, so I'm going to set it false. But this condition is met, maybe I'll set it true or in a false. And I end up with a Boolean value at the end. And that's the Boolean condition pattern. And again, you use, they're very similar, but one's doing as you go and the other one's saving the doing part at the very end. There's probably an electrical circuit equivalent. So one kind of circuit to do one and another kind of circuit to do the other. Finally, what do we got here? Compound distat. Now see, I slipped into Fortran. The I/O was so complicated that I had to elevate myself up to Fortran. I did one instruction. I knew there wasn't going to be a lot of I/O because it was like this paper tape thing. So I could slip into slow old slug of a language like Fortran to do I/O. And once I got into there, I did a little more dispatching. And this is when you're doing I/O, on a big computer, you don't just move a byte. There's no byte addressability. Everything is a word of this, a word of that. And by the way, characters were 6 bits back then. And you had to walk uphill to get them too, right? So the buffering was important. In operations, this one's kind of cool. This was something that, I don't know, I think people who wrote this kind of stuff knew it, but we called it a command loop back then. And this is almost what we call a read-eval print loop or a REPL. But, I needed a front panel. And I didn't have a front panel, so I made a little language that says, well, put the tape in the tape reader and take the tape out and turn on the punch and whatever. I had commands like that to operate the computer. And that was my outer loop, command loop. And this one, also, every command ended with the same stuff, so I would jump to the end. If this were recursive, it'd be called tail recursion, but this is just sharing the tail. And back then, you jumped to wherever you needed to be. There's none of this one entrance and one exit. It was jump anywhere. And so I was a good citizen just by having the code in order. So anyway, that was the experience. I hope you get a feel for the kind of stuff that's in my mind continuously when writing this program. I was very proud. I mean, I wasn't writing this for a grade. I just wanted to be able to do assemblies any day of the week. And I didn't want to have any bugs. So I had the set of patterns. I'd written enough code. I knew if I just did them carefully, conscientiously, the code would work. And you know what? It didn't work. I put the assembler in and it didn't assemble. And I hadn't planned on that. But I knew a guy who worked over in the psychology department where they had a lot of these computers to control experiments with mice or something. And he maintained them. So I went over there and I said, well, how do you fix your computers? And he says, well, I got 2 classes of here's the machine diagnostic and here's the whole operating system. Give me the machine diagnostic. I got a tape, read it in to the CDC, ran the DEC machine diagnostics against my simulator, and it says your skip on non-zero instruction isn't working. And I went and checked, and yeah, I got the if test wrong. So I corrected one bug, and it worked great. One bug in 600 lines of assembly. And so I thought that was pretty cool. Now, in 1995, I put this up there, and people kind of catch on to this. There's the cult following in PDP-8s. And somebody said that I misunderstood how the index registers work. And I had to admit that when I looked it up in the book, I'd coded a second bug, but it was a bug that was not exercised by the assembler. So, it met my criteria. And that was pretty cool. I also thought that this was an interesting activity. And I mention it here because I think this is the kind of group that would be interested in technique. You know, a lot of these, you know, there's a lot of Bart's, I keep looking at Bart because he gave a talk that was really about technique. He didn't call them patterns. He would have, you know, if he just, but it's if you don't have technique, and I was going to put something about this new, you know, what is it? It's the bleeding heart, heart bleed. Oh my God, you know, well, there's a little bit of technique there that somebody just missed, and so like 60% of the, you know, the internet is broken.
No big deal.
No big deal. But I decided not to mention that. But I do want to mention that the simulator is still up there on the web in classic HTML. And that was restored in 1998. I have the actual PDP program up there too, and it's not restored. You'll have to get a manual and figure out PDP-8 yourself. But I might get to it someday, to be restored. But I have, in the back of my mind, keep thinking, gosh, it's getting better and better. The internet is so powerful, and with this JavaScript and stuff like that. And I know people do, like you can, you know, pretty much any console has been hacked in JavaScript at this point. But remember, I'm about understanding it. So I need to like recreate these programming environments, but better than the old days, so that you can, like in an hour, understand what it was like to spend a week or a month or a year programming. And I think that that's interesting. I also decided, and this is, I do this federated wiki, so I always have to pitch it. This is a wiki I made called Code on the fed.wiki.org, where I just found out it was easier just to reminisce. So I decided to have one page for every program I ever wrote. And there is, if you go there, it says it's called the coding portfolio, and if I click on that, oh, I didn't even click on it. I just said search for PDP. And it says, well, gosh, you have a bunch of PDP pages, but one there says the PDP-8 simulator explained. And when I wrote this just a year ago, I realized, well, I'm restoring the restoration of the PDP-8 simulator, and I think that's really, you know, getting mileage out of your software. Definitely worth doing. I analyzed how many different files I had to make to have all those different things pop up. I don't have to do that now because I got this new super cool wiki, and this is one I talked about last week. I was speaking here last week, and it's been videoed. So, and that's the Colossal Cave Adventure. And they recently uncovered, like a couple years ago, the original version of that, incomplete by a single author, Will Crothers. And he was a caver who was just trying to make something that was an authentic experience of being in a cave. And in the process, he made a computer program that had never been made before, interactive fiction. Now we do interactive friction. Interactive fiction. And I said, well, I just want to feel what it was like to be programming at that level in these old languages. He used Fortran, just like this other thing did. And so that's a bunch of pages. I start out at the east end of a long hall or whatever. You can roam around in the cave, but then you very quickly find yourself roaming around in the code. And he even said later on, he says, well, people like this game because programming and caving have a lot in common. You're just trying to find the right thing, well, at least the game, the right word to say to get done what you want to get done. And so I think that this experience, there's a lot of stuff that's old and it's interesting to experience. Certainly digging up that, you know, lunar module thing would be awesome. There are plenty of Google people there to help too, because they did the lion's share, and they even got a simulator, but they don't have a pattern analysis yet of what it's like to be at MIT. Charles Stark, whatever the great inertial guidance people there at MIT, figuring out how to do all that stuff at the dawn of the space age. And that's restoration of old programs and the patterns used therein. So thank you. Any questions? How do we do time-wise? Was that 25 minutes, 30 minutes? I'm sorry, I said 20. Yes?
Did the PDP-8 have a decent Fortran compiler? And I asked because my first code was on PDP-11 Fortran.
PDP-11 was fabulous. PDP-8, it didn't really do that. Wasn't big enough. They might have had a Fortran, but I don't know anybody who used it. Although they had this really cute language that they actually had a time-sharing system would run on one of those things, and it would support 8 users running Focal. And Focal was like Fortran, but every command was 1 letter, so you could fit more on your tape. And but it did floating point. What's that? Did you?
What's the most famous Focal program of all time?
Probably Hammurabi.
Yeah,
Hammurabi.
Far
Yeah.
away.
Well,
Oh yeah, everybody else knows. Never seen it.
Hammurabi. Does anybody know? You're.
No, that was a translation from the original Focal, believe it or not. Yeah.
Yep. So yeah, definitely. Well, we got to get Hammurabi done in Federated Wiki. Other questions? Yes.
Chico?
Tico?
TCO?
That's an editor, right?
Yeah,
That'd be a great one.
yeah. That's the PDP, predates the PDP-8.
Yeah, I would believe that. Yeah. Yeah, the PDP-1 was the first of the PDP series, and before that there was like Lincoln Labs had some crazy machine that just changed every week. And yep. TX0, right?
Yeah.
Yeah, so if you get into your old machines, but knowing what it's like to program, it turns out that Alan Kay, who invented Smalltalk and ran this fabulous lab, had his staff all study, what's the graphics program that ran on the TX2? It was I'm blanking on it, but there was a graphics program that had object-oriented in it. It had direct manipulation in it. What is it called? Sutherland's. It was Sketchpad? Yeah, he's here. Yeah, he's your bud, right? Yeah, well, they dug out that old code and studied it before they worked on Smalltalk, just to admire what had been done there. And then they asked Sutherland, they say, how could you invent object-oriented programming, direct manipulation, and constraint solving all at the same time when people were still trying to figure out what a computer was? And he said, well, I just didn't know it was hard. So there you go. One last question?
So when you did this exploration, I mean, do you build tools? Is there technology, technique? I mean, you obviously have built some stuff that makes this easier to at least write down.
I can't quite remember, but I didn't save any scripts in 1995. But I was writing a lot of Perl, 98. Now what I do is I've written lots of translators that read any old stuff, build a structure in memory, and then board it out as wiki pages. And I do that so often. Like I'll read spreadsheets and board them out as wiki pages. So that was just let's board it out and see what it looks like. And then once I'm looking at it, I say, I could add another if statement here, and then I'll get a little more out. So I just coax more out. And that was a tool. I wrote one tool to read the map of the cave and put in the cave pages. And then for some reason, instead of extending that, I said, well, I'm going to do the code in a different tool. And so I had 2 tools. And then I thought, well, gosh, when you want to get to the cave where the choice depends upon the code, so instead of actually doing the work of putting it together, I had the code program drop out a little JSON blob of where all the statements were that the cave, so there'd be a little bootstrapping problem of getting them running again. But, I'm doing this an hour here, an hour there on the weekends. And it's just fun. And it turns out, I mentioned this to my brother, so he digs up a version of the very popular version that was done by Crothers and Woods, and has that running in JavaScript. And I mentioned, well, that's not the original. And he says, oh God, I want to play the original. You know, why would you play, you know, second generation when you could get the original? And so we're talking about, well, you know, Fortran's not that complicated. You know, we could probably do a series of regexes and translate that to JavaScript pretty easy. And the two places we couldn't do it, we'd just do by hand. So we'll do it, you know, and that's because he wanted to. I said, I don't want to play it, I just want to experience it. He says, oh no, let's get it working. So, you know, it's infectious in that regard, especially when it's your own old programs. You got to get older, you got to have a white beard, and then you can dig into this. There's a few of us nodding like, oh yeah. Yeah. All right, well, thank you very much. I appreciate it.